Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. Last class we stopped with discussion of flow over a wedge with the angle more than critical angle. Angle more than critical angle, and we said that the flow will have a bow shock, and this flow is more complex. It is going to have subsonic pocket, and then the flow accelerates to supersonic across it. And we said that the shock angle, if I go along this line, starts from 90 degrees, decreases to all the way up to Mach angle. All that we did last time. And then we said if the gas becomes more compressible, then this, that is, I gave an example of gamma less than the previous gamma. If gamma decreases, then I said it is roughly more compressible. That is not the only way to make it more compressible, that is one of the ways of making it more compressible. If I decrease my gamma, we said that the flow has a possibility of having this as attached shock. Okay. There is also a possibility of it just decreasing to some other bow shock where the standoff distance has now decreased. That also is a possibility. This is something I did not tell last time. That is also a possibility. If my compressibility is increased only a little bit, it goes closer to the body, it need not become an attached shock. If it is sufficiently low enough, then the gas inside in this region has been compressed more and it just goes in fully. If the shock has gone in closer, then the subsonic pocket would have decreased, it will be even lesser, remaining portion will be all supersonic. Okay. That will also happen. Let us just mark this as 1, 1 and 2 and 2. This is more like what it will be. Okay. And eventually it will go to a point where the subsonic pocket will go to a point, and then the shock will just become an attached shock, and we know that that shock will only be a weak oblique shock. While if it is a bow shock, I start with a normal shock, go through a strong oblique shock all the way somewhere up to here, and then from here it is weak oblique shock all the way up to Mach wave, which is supposed to happen at infinity. All that will happen. Okay. Now we already said that there is no analytical way of solving this, so we will just say that if such a thing happens, we will just say I do not know what to do in our simple inviscid gas dynamics, we will just stop this. Ideally there are methods by which we can do CFD analysis and solve this problem. We will not do it right now. Okay. We will say we will not deal with such problems currently. We will just skip that portion and then go on to another part of oblique shock problems, where I want to think about, I want to see what happens when I created a oblique shock from here and it is encountering something else. Okay. It is going like this and it say it sees a wall. Now what will happen here? This oblique shock, what will happen to this from here? Okay. And if you have ever seen any books, you can tell that it will just reflect off the wall. It will not be reflecting like a simple light ray reflecting on a mirror, it will reflect slightly differently. To understand this problem, it is basically simple problem of just one oblique shock at a time. Just keep this one picture in mind. If you want to solve any problem like this, always remember this one picture, which is the basic oblique shock picture, right. If there is a flow this way and I have a deflection of theta and I am assuming it is attached oblique shock right now, and it is going like this, and I am going to give an angle for this beta. This is the basic oblique shock picture we have been thinking about all the time. Just remember this always. Okay. Am I drawing it correct or wrong? How will I check? Remember piston analogy. We just said piston does not move all the way till here and suddenly piston starts moving from here. As the piston goes in, there is a shock that goes in earlier. We did this as an animation some time back, you can go look at that also. Okay. So since the wall is going into the flow, see streamline is going like this, the wall is moving into the flow, it will cause a shock. Okay, remember this. You will need to remember this one statement when we go to expansions, okay, which will start after finishing the shock reflections. So, if I take this particular case, I do not want to disturb this picture, I will keep this picture, I will go to the next one. Let us say I have this particular flow situation and I have an oblique shock going like this. Okay, and there is some supersonic flow incoming, and I am going to say this basic problem here is just same as what we did here, exact same problem, no difference. I will just copy stuff. The streamline here will be parallel to this wall. So, I will just go and copy this there, I will just put lines like this. Up to the last streamline where the shock goes and touches the wall, all the streamlines want to turn like this parallel to this wall. Now, after this, now I have to figure out what is happening when this set of streamlines go and hit on that wall. That is a new problem. The way to look at it, I will use this paper, I will just cover this region. Now, what do I see? I just see streamlines going like this, hitting on that surface, that is all I see. I will draw it as a fresh image, a fresh picture here. It is as if there is a flow like this and it is encountering a wall like this. This is the way to look at this problem. Whatever happened before has already happened and it is all done. Now, we will say after this shock what will happen. This is a new flow, we know that it is also a supersonic flow because it is a weak oblique shock, it is again going to be a supersonic flow, and then it is going to go impinge on this surface. Why will it impinge? I am going to imagine another problem. I will just put a line along this and imagine a wall like this. This wall is parallel to my streamlines. In inviscid flow, I can always put a wall parallel to any streamline and it should not cause any trouble, right. It is not going to have a boundary layer, I can always imagine a wall there. So, let us imagine a wall there and the flow is going parallel to the wall. Now, suddenly there is a deflection of that wall this way, right. What will be this angle? We can find that angle also, and if I go look at geometry, I can tell that this deflection angle will be the same as that deflection angle back here, because it started from here, it went up some angle, it has to come back parallel the same amount because this wall is same. So, it will again be your theta, okay. But this Mach number is m2. So, now I will mark every variable now. This is m1, this I will now call beta 1 because now I have a new shock. This is theta 1 and this is theta 2. It so happens that this is equal to theta 1 in this particular geometry. And so, now I am having a problem which is basically there is a flow and there is a wall moving into the flow. Okay. If I go back and look at this problem, it is roughly same as that figure except for I am looking at it upside down. Okay. The same figure, I just look at it upside down. Okay. If I turn the page and look at it from behind, it will look something like this. So, I will have a shock that is going to go like this and this will be its beta value. Okay. Theta 2 is same as theta 1, but m2 is definitely less than m1, right, because that is what it will be from a oblique shock, and beta 2, if you go and calculate, it will be more, beta 2 will happen to be more than beta 1. Why? Just from looking at simple theta beta m curve. Let us say I picked this particular theta, which is our theta 2 equal to theta 1, let us say this is my theta value. What I am seeing is, let us say this is my m1 and after the first beta value it jumped to a m2 and you will find that the beta has increased directly. This is direct proof, you have to get used to these kind of numbers. If you are doing numerical examples, if you make some mistake here, things will go wrong. Okay. So, just remember this kind of figure, it will be very easy to understand it. Okay. So, this will be the situation. Now, what should I do? This is just a example problem. The actual solution for this problem is I have to put that back inside here. So, there is a shock there with this beta more than the previous beta we said, which means I have to make sure that this angle with respect to horizontal is less than the new one I am drawing with respect to horizontal, and it is coming from the top downward. So, I will go more like this, more steep. I will erase this for avoiding confusion, that is streamline. Instead I will put one here. Okay. So, this is what it will do here, and this angle, not this angle, sorry, it is from that line, original line, it is beta. Actually it is going to look more like that. I will correct it so that it is easier for me to go for the next one. It has to be like this. With respect to this line, I will draw that dotted line parallel to this, which was your original wall. From there it turned in, this is your beta 2, and this can never be more than 90 degrees. The way I have drawn it, it is close to 90, but let us assume that it is less than 90. It is supposed to be slightly there, it is more correct. Okay. So, this should be less than 90 degrees, because we know we are in weak solution, it should be probably less than 60 degrees or whatever, but we can find out the exact number if we have the chart anyway with us, and we showed the chart last time. I will put it up on the web for everybody to use later. Okay. So, it is going to have something like this. Now, what do I do with the next shock that is coming here? Again the exact same problem repeats. I am going to, what is this duty of this shock? It is going to turn the flow parallel to the new wall, which is your original horizontal wall, this wall. So, it is all going to go this way now. Now, what will happen? The whole problem repeats at this corner now, and then it is going to go again, bounce off up like this. Okay, it will bounce more at this angle, it will bounce off like this. Okay. That is what it should do, assuming some things. We will look at that later. Okay, we will get back to that when things are going past the critical angle. Okay. We will look at that case separately later. Okay. If I look at simply a simple model, let us say this is my model kept inside a supersonic flow, and this is my tunnel wall, and there is m greater than 1 flow coming this way. Now, I can think about shocks that are going from here, assuming it is attached shock, and then it will bounce off and come back. This is what will happen. Okay. Of course, I am not talking about what happens in this corner, which we will deal with after we understand expansion. There will be expansions here. We will understand that after we deal with expansions, which will be the next section we will deal with. Okay. So, as of now, we will just say this shock is going straight, and then it is bouncing off that corner and coming back like this. That is what will happen in a typical supersonic tunnel. What if my angle is more than critical angle? Let us say I put such a model. If I have a model with angle more than critical angle, then I will have an oblique shock sitting here, which is same as whatever we discussed last class and today at the beginning. After that, this is going to be some shock, oblique, weak or strong, depending on how close the wall is. Let us say it is weak oblique shock. It is again going to bounce off like this. Even here it is going to reflect off this way. We will not worry about what happens if this comes and hits here, it may reflect again. Okay. That could also be a case. We will not worry about that. If I pick this particular problem, and if I imagine my piston analogy, I just look at only one axis line. Let us say I draw an axis line for this. If I draw an axis line for this, if I think about piston analogy, I will look at only the top half of my picture. As it comes, there was no piston for this vertical fluid element, it is just going straight like this. Suddenly a piston starts moving upward, which means there will be a shock going in front of it, ahead of it, and that is what is happening here, it is moving ahead of it. And then later it finds that the piston, that cylinder has a top wall closed. If I think about that way, then this shock goes, hits and reflects back. This kind of problem we already dealt with. Where did we do this? We had a case where I have a closed tube and there was a flow coming like this, and this there was a piston moving like this. We did this problem, I believe. We had a piston that was moving inside the cylinder, which caused a shock running in, and that caused flow behind it, and then eventually when the shock goes and hits there, it will go hit, bounce and come back this way with another shock, and all the velocity here will become 0 again. We did this problem as an exercise example problem, we did numerical example, you can go back and look at it. This is the kind of analogy I am going to imagine. Just take the cylinder, put it vertical and put it here and let it move along like this, similar to our animation. You will find that the shock goes there, reflects on the wall and comes back. That is what will be happening in this place. Okay. One caution though, piston analogy does not always work. In fact, it does not work in this particular case. Okay. When my shock is detached shock, piston analogy breaks down, because now even before the piston starts moving, or in our case the wall starts changing, we see that there is a shock. This is no more a simple 1D analyzable problem, this is purely a 2D problem with subsonic solutions also present. Our piston analogy does not work very well for any detached shock cases. Okay. But remember this simple picture. If I have a wall changing thing, then there will be a shock produced there, and this is the procedure for analyzing it. Whatever we did now is the procedure for analyzing such flow fields. Okay. That is the idea. Now we will go and consider a case where things go wrong. Okay. The next question will be, I go to this case, I have the same flow situation, but let us say my Mach number is different, and now it is such that this theta is greater than theta critical. What will happen in this case? This is actually already solved problem. We did this before. What will happen? It will not have an attached shock ever, it will just directly jump to a detached shock in front of it. It will look like this. Okay. This is one possibility. This is nice and simple possibility. I just wanted to recall this before I go for the more complex case. Let us say I keep this picture, I will draw once more. I have a case where I have m1 coming, and this theta 1 is less than theta critical based on Mach 1. So, I will call it theta 1, theta critical 1 also. Okay. And so, it is having an attached shock, it goes there. Now, we will go and do the analysis. I have incoming flow, this is a new direction, and I will block this with my paper, and then what will I see? I have a flow going like this, and it is hitting a wall which is facing inward. This must be the original direction, from there it turned by so much. Okay. Let us call this our theta 2, and this is your m2, right. It started with m1, it deflected by theta 1 and it produced m2, and this is your beta 2, sorry beta 1, sorry this one, this is your beta 1, and from here I am going all the way there. Now I block this portion and I look at only post shock flow. What do I see? I am seeing flow going this way, I will draw a dotted line parallel to this, and from there it is deflected by theta 2, which means the wall is coming into the flow, which says that there will be a shock. Okay. If there is a shock, it has to be from there some beta 2, and we already know that beta 2 will be more than beta 1. I have drawn it such that it is more. This should be the case. right. This is same as whatever we did before in here, exact same case. Now I will put a small trick. I do not want this condition to be as simple as that. Okay. I am going to say this theta 2 is greater than theta critical for M2, if I have such a case. Now I cannot draw this, beta 2 is not a well defined function anymore, beta 2 does not exist. Okay. So there should be a bow shock for this wedge alone, if I think about it. So with respect to this flow, I will go back and listen to this one. I just look at this, flip it over and look at it, then you will see. I will draw that for easy imagination. It will look like this. Okay. This should be your picture finally. Okay. If that is the case, I have to tilt this slightly so that this wall becomes parallel to this dotted line. If I do that, then I will end up with a shock. I am having too many, this is causing more lines. Okay. Anyways, so I have this original dotted line. This is what is imaginary wall for the post shock flow field, which is going like this, and that angle is more than critical. So there should be a shock that is going like this. This is what should happen if I look at this picture with this slightly rotated. If that is the case, what happens to this shock? That should merge with this one and form something new. Okay. So I have come to a case where when this oblique shock goes and hits and it has to reflect, but the reflected solution should be a bow shock. If I think that, then my solution changes. I will just erase some parts of it, because the post shock solution should come ahead of the previous shock, which means I have to erase this shock up to some region and I will redraw it. No more beta 2, so I will erase that beta 2 arc, everything else stays. This is much worse. And now this is how it forms. It is roughly true. I cannot give you the exact shape. The shape depends on the exact problem, and it is not very easy to solve this problem. Okay. It is again similar to bow shock solution. This is a complicated bow shock attached with the already existing oblique shock. This is what it will finally end up with. What is happening here is there is roughly a normal shock sitting here, and then there is somewhat curved shock sitting here. Okay. This is what is called a Mach reflection. Again, Ernest Mach was the one who explained this very well. Okay. He explained it for blast waves traveling across wall, okay, but anyways it works very well for our case also. This is shock reflection at a wall, that is explained like this. Okay. It could be any of those reflections, all the reflections were explained first by Ernest Mach. Okay. Anyways, I am going to have this case. What is going to happen here? This is a normal shock, flow goes straight, it sees a normal shock, it slows down, becomes subsonic, here it is m less than 1, and it just goes straight. Okay. Here it is m greater than 1, m1 greater than 1. Here it is forming some m2, which is all a fixed value, because it is a straight single line oblique shock. After here, this is going to have different Mach numbers in different points. Okay. It will be slightly curved shock. It is not very clear how to explain this very well. Okay. It just becomes a complicated problem to solve after this. And there is one more feature to this. I will draw this dashed line. It will go roughly like this. It is supposed to be a single line going straight along at an angle. Okay, it is going slightly towards the top one, towards the subsonic side. This is a slip line, that is, this is a line across which velocities are not matching. Here the velocity is higher than velocity here. So the fluid elements are slipping along this line. Why is it slipping in this case? We do not have viscosity. Okay. No viscosity case, fluid element can slip across each other. Only when there is viscosity, there will be a gradient and it will start decreasing gradient. Anyways, so because of that we see that fluid element here is having a very high velocity and this one is having lesser velocity, and they can just go as if nothing went wrong. Pressures across here will still be matched, okay, velocities will not be matched. Okay, that is one thing I want to tell. Next thing, just notice this region, since the flow is going along this line, okay, this is also a streamline, this is a slip streamline. Okay. Since this is a streamline, what is going to happen to this stream tube? A streamline that goes through this and then it is going along this line. What is happening here? This is a subsonic region and it is seeing that the stream tube is getting compressed. This is the wall, remember that the top line is your wall, top line is your wall and this is a streamline. Wall is also a streamline, right? Flow has to be parallel to the wall. So, it is going like this. Now, you are seeing convergent duct for subsonic. What should happen? Flow should accelerate. Okay. So, the flow here is going to accelerate. What about the other section? Okay. Here there is possibly a region, I am not sure about what will happen in this zone, probably there is some subsonic region, but mostly it is all supersonic region. Okay. Most of these regions are supersonic, where it is going to form supersonic flow and it is going through a converging duct. What will a converging duct do to a supersonic flow? It will decrease Mach number, it will go towards m equal to 1, all converging ducts. Okay. So, it is going to decrease Mach number here and it will increase Mach number here. What is essentially happening? This flow is slowing down, this flow is accelerating, they are all kind of trying to come to a single Mach number. Okay. That is what is happening there. What will happen to this shock when it goes and hits here? Depends on how strong it is, it may bounce off again. Okay. I have not seen much cases where it bounces off several times, it may bounce off once more and by then viscosity will come and eat it up, you will not see it much. Okay. But here in inviscid world it should bounce off again. Okay. And we have to worry about, will this Mach number be okay or whatever, we have to think about one more round. Okay. Oh, I drew this final angle wrong, it should still be parallel to the top wall because this reflection is coming for this wall, it is going to be close to that, but it may be slightly tilted. And now this wall, this streamline will go and interact with this bottom wall and it will again bounce off from here because it is seeing a wall going through the streamline. So, it will again bounce off one more round, that is a possibility. Okay. If there is viscosity, these things will not happen this well, okay. There will be more difficult thing to solve. Now, overall this particular problem I am showing you all this, but it is very difficult to solve from our gas dynamics. If I go and simulate it, I cannot get analytical solutions for this. If I go and simulate it in some CFD programs or numerical algorithms, I can solve this problem exactly and I will get some nice solution for it. Okay. But I cannot give you an expression saying for this much height it will be a normal shock, after that the shock will start curving like a bow shock, I cannot tell that from here because similar to bow shock, all the same reasons, it has transonic region, subsonic region, supersonic region, everything together, it becomes more complex problem to solve and we will not solve that right now. Okay. That being said, I have given you enough whatever feel for oblique shocks and normal shocks already. Now, it is time to go to expansions, but before that I thought I will give you some numerical examples so that it is complete and I can give you a separate exercise for solving for this later. Okay. And of course, go and look for exercises next to the video on the website, we will give you those also in time. Now, we will start with numerical example. First example, very simple one. I am having a 15-degree wedge, okay. That is its half angle is 15 degree, it is 2D problem, okay. And my incoming Mach number is 2, it is 1 atmosphere pressure, static pressure P1 equal to and T1 equal to 300 Kelvin, okay. And we want to find all the properties at this point close to the wall on the wedge, okay. That is the idea. Basically I want to find, let us say I have to start with find the beta, the shock angle, M2, P2, T2, P02, T02. Let us say I want to find every variable there. Okay. So how will I find this? I have to go and start with, this is my theta. I know that theta equal to 15 degrees, but I do not know beta. I will just draw a line. This is my beta, I need this. So I have to solve this for beta. How will I know the beta? I have to go back to my theta beta m curve. Okay. If I go look at the charts, I have a gas tables which gives you the chart for a particular Mach number for a given deflection, it will give you the beta value, or you can just go use the chart. I typically use the chart even though I have the table. Okay. I typically use the plot, not the chart. So okay, I will go look at that, and I am getting beta value to be 45. To some extent it will be correct, it could be like 45.25 to 35 somewhere there, I just put 45.3. Okay. And it so happens that I interpolated on my tables and I got exactly the same number also. Okay. I have this. Now I have to find, once I know this I can solve the whole problem. Once I know the beta I can solve the whole problem. M1 normal, it is given as M1 sin beta, which is 2 sin 45.3 degrees, okay, which happens to be 1.42. Now the problem is simple, I have converted this to a normal shock problem. All I have to do is go to normal shock tables for gamma equal to 1.4, find that all the properties across the shock. So I will get P2 by P1 is equal to 2.186, which implies my P2 is equal to 2.186 atmospheres, because P1 is 1 atmosphere, okay, and T2 by T1, I will just directly write T2 equal to 300 times 1.267, that is going to give me 380 Kelvin. That will be the temperature across the shock. Okay. Now I will find Mach 2, M2. M2 in normal shock tables will be called as M2 normal in my oblique shock. Okay. M2 normal happens to be 0.731, which is equal to M2 times sin of beta minus theta. Beta is 45.3, theta is 15, so I will put 30.3. 30.3 degrees. Okay. So when I use this and find out my M2 value, this thing gives my M2 as 1.449. That is going to be my M2 value. Okay. Now we know beta, we know M2, we know P2, we know T2. We need to find, let us say I do T02. What will be the T02 value? T02 across a shock supposed to be a constant. Okay. T02 does not change at all. Okay. T02 is same as T01. T0 does not change at all. Sorry. Okay. T02 is same as T01. It just stays the same. Does not change. Now I will just do the P02 by P01. Okay. This is where we said we have to be careful, right? We said you have to do the normal shock P02 by P01 and then use that number as P02 and then solve for the whole case. That is what it should be. Okay. P02 by P01 happens to be 0.955. Okay. From here we can find P naught, oh I did not find the P naught 1 actually here, okay. P naught 1 by P1, I have that value, but I have not calculated the whole thing, 0.128. So I know P1 is 1 atmosphere, so I can find this number, that multiplied with this must be your P naught 2. I did not find that final number, which I believe you can find out, it is not very difficult to find. Okay. Okay. Now I am going for another example. Where we want to find shock reflections. I am going to pick a problem where it looks like this. I want to solve this problem. Okay. And we will first worry about the first part. Okay. I am picking M1 equal to 3, theta 1 equal to 20 degrees. I am picking this, and currently we will say that I am having a reflected shock, and I picked a wall geometry such that that shock comes and meets this. Otherwise, the problem becomes very complex. We will deal with that problem later after a long time. Okay. Currently, let us say there is a reflection and it goes and meets this point exactly. What is the advantage of that? Flow goes like this, turns like this, and goes back straight parallel. Same thing happens here also. There is no more problem about it could be an expansion that is happening in the corner, which we will deal with later after we deal with whole set of flow fields in supersonic flow. Okay. We are picking this particular special case. We want to solve flow field through the whole region. Okay. If I pick this and I am giving the same thing, P1 equal to 1 atmosphere, T1 equal to 300 Kelvin. I am giving you the same condition. Oh, here I have found P naught 1, but this is a different Mach number. P naught 1 is 36.76. Okay, this is given. So now to start the problem, I have theta 1 and I have M1, so I can find beta 1. Not very difficult to solve. So I go to the chart, the plot, and I am going to find that my beta happens to be 37.8 degrees. Of course, there is some error in reading out. When I look at the data tables, I found that this number was 37.75 degrees. Yes, of course, there is some error. Let us live with that error, it is fine. We can still give reasonable accuracy what has happened. Okay. If I use this and I find my M1 normal, this is going to be Mach number M1 times sin beta. So, it is 3 sin 37.8, that is going to give me a number of 1.837. That is going to be a number. Okay. Now, I have to start with normal shock tables, and I have only 2 decimal place accuracy. So, what I will do is I will interpolate for the 3rd decimal place accuracy between the 2 values. I have numbers for 1.83 and 1.84. I will interpolate 70% between these two. Okay. So, I am getting a whole set of numbers from normal shock tables. M2 normal is 0.608. P2 by P1 is 3.769, T2 by T1 1.560, P02 by P01 0.796. Okay. I have a whole set of numbers just read out from that one row of data. So, from this set of numbers I can find my actual Mach number M2, which is going to be 0.608 divided by sine of 17.8 degrees, that comes out to be 1.994. Okay, this is a very special case. Mach 3 with 20 degrees gives Mach 2 behind it. Okay, it is roughly that. It is a very nice number to remember. And P2 is 3.769 atmospheres, T2 is 468 Kelvin, P02 is 29.26 atmospheres, and T02 does not change, it is the same all over, you do not need to worry about that. Now I have a new problem to work with. What do I have? It will be the same deflection back here. The flow is going like this, 20 degrees above horizontal, and it has to go back to horizontal. So I will again have a 20 degree deflection, and it is again going to be a compression wave. So it is going to be another shock. So I will put a theta 2 equal to, till here it is one shock problem. After this I am going to the next one. Theta 2 is 20 degrees, and we have M2 is 1.994. Okay. So with this I am going to use my chart, and I am going to get beta value roughly 53.6 degrees, okay, roughly 53.6 degrees, and this is going to give me my, I have to call this again M2 normal because the original one is called M2, but I will put a prime here because this is a second reflection M2 normal. This is not the same as the previous M2 normal. Okay, just at this moment, when once I go to M3 normal I will not care. Okay, this happens to be 1.60. Now I am going to go to normal shock tables, use this number, read out all the data from the row. M3 normal is 0.668, P3 by P2 is 2.82, T2 by T3 by T2 1.388, P03 by P02 0.895. I have all these numbers, okay, and from M3 normal I can immediately get to my M3 value by dividing by this minus this sine of that value. Okay, that is 33.6 sine. I will divide this 0.668 by sine of 33.6. I have done that, and that number comes out to be 1.207. Okay. And P3, we already have P2. I just have to multiply with this one, and P3 is 10.663 atmospheres. T3 is going to be 650 Kelvin. P03 is 26.19 atmospheres. And I did a quick check by seeing whether if I use this M3 and this P3, will I get this P03? It should also match. I got this P03 from this data from my M2 normal prime. Right. If I go and calculate it another way, I will just use isentropic tables and calculate based on this Mach number and this P3, what do I get? Okay. If I use that, P03 equal to P3 divided by P3 by P03 at M3. If I do this, that number, oh yeah, 10.63 divided by, I am going at an angle, ignore that for now, divided by 0.406, and this number comes out to be exactly 26.19 atmospheres. Okay. I had two ways of calculating P naught across the shock, and they give the same answer. Okay. So, I can use just M3 P3 and then use this with isentropic tables to find P naught 3, that gives the same answer, or I can use this P naught 3 by P naught 2 across that particular M2 normal, and that will also going to give the same, but this is going to be from normal shock tables. Okay. I can get to the same exact answer. Okay. We have around a few more minutes. I will just give you an example where things go wrong. Okay. Let us say I will pick similar configuration. I am putting theta equal to 23 degrees now, the same m equal to 3, same problem. Okay. Now, I will find that for this case theta equal to 41.5 degrees. Compared to the previous problem, it is slightly higher angle, so this number is also higher. Previously it was 37 and now it is 41, okay, slightly higher number. Okay. Now, from here I am going to find m1 sin beta, this comes out to be 1.988. M2 is going to be, I am cutting short some steps here, M2 is going to be 0.58, this is your M2 normal divided by sine of 41 minus 23, okay, that is 18.5 degrees here, and this number is 1.83. Okay. Of course, I could also calculate P2, T2, P0 2, everything, but let us say I want to avoid all that. Okay. I just want to see what will happen. The flow from here has now turned with a Mach number of 1.83. Okay. That is one new Mach number, and that is again facing the same deflection 23 degrees. That is your theta 2 now. Okay. Theta 2 equal to 23 degrees, and my M2, the Mach number here is 1.83. Okay. Now, if I go and look at this particular problem, it so happens that this is past the critical angle. Okay. For this Mach number, theta critical for M2 is of the order of 1.9. Sorry, 1.9 is the, it is of the order of 20.5 degrees or so. Okay. For this case, 1.9 is your Mach number from which I got this data, 20.5 or so roughly angle. Okay. Because of that, now I am not going to have this angle deflection ever possible using an attached shock. Okay. If this is happening, then I should have a bow shock here for that problem, which means this problem is solvable up to only this part. After that, I do not know how to solve this problem using these simple gas dynamics. Okay. After that, the problem will look something like this, and this should be your final answer. Till here I can tell 1.83 Mach number, I can tell from here. After that, I do not know where this will start, I do not know what is the height of this in this whole picture, okay, and that is all I can say at this point. Okay. So, we have come to a point where we have given some example problems of oblique shocks, and I will give you a lot more of these problems later. The next important thing I have to think about is expansion waves, okay, how expansion waves affect flow field, and we will start with that next class onwards. Okay. See you people next class.